Section. Introduction. In this report, we introduce an enhanced version of PIXART, a high-quality text-to-image synthesis model known for its superior image generation and efficient training process. This new version incorporates two key components: the Latent Consistency Model, LCM, and ControlNet. The LCM is integrated into PIXART to speed up the inference process. It allows for high-quality and fast inference with only 2 to 4 steps on pre-trained latent diffusion models, LDMs. This is achieved by viewing the reverse diffusion process as solving an augmented probability flow ordinary differential equation, PFOD. As a result, PIXART can generate samples within approximately 4 steps while maintaining high-quality generations. This leads to a significant improvement in the inference speed, making it 7 times faster than the original PIXART. We also incorporate a ControlNet-like module into PIXART. ControlNet is known for its superior control over the outputs of text-to-image diffusion models under various conditions. However, replicating it directly into a transformer model is less effective due to the intricate design of ControlNet for U-Net-based diffusion models. Therefore, we propose a novel ControlNet transformer architecture customized for the transformer model. This new architecture achieves explicit controllability and high-quality image generation. The consistency model, CM, and LCM have significantly advanced the field of generative model acceleration. They have introduced faster sampling techniques while preserving the quality of generated outputs, paving the way for real-time generation applications. ControlNet, on the other hand, allows for the manipulation of input conditions, enabling control over the overall layout of the generated image. It introduces a special structure, a trainable copy of U-Net, that integrates the outputs of each layer of this copy into the original U-Net using zero-convolution layers. This approach effectively prevents overfitting while preserving the quality of the pre-trained U-Net models. In the next section, we use latent consistency distillation, LCD, to train PIXART on 120K internal image text pairs. We provide a detailed training algorithm and study on specific modifications. We also illustrate the training efficiency and the speedup of LCM of PIXART. The LCD algorithm is derived from the original consistency distillation, CD, and LCD algorithm. It involves 3 models, teacher, student, and EMMA model, that function as denoisers for the ODE solver. During the training process, we begin by sampling noise at a certain time step, where the teacher model is used for denoising. We then use an ODE solver to calculate from the sampled noise and the denoised output from the teacher model. The EMMA model is then applied for further denoising. In parallel, the student model denoises the sample at the same time step. The final step involves minimizing the distance between the outputs of the student and EMMA models, also known as optimizing the consistency distillation objective. Our study also examines the effects of 2 key aspects of the LCM training process: the CFG scale and batch size. We find that using a constant guidance scale, instead of the more complex CFG embeddings, improves performance in PIXART and simplifies the implementation. We also find that larger batch sizes positively influence performance. However, PIXART can also converge fast and get comparable image quality with smaller batch sizes. Finally, we adapt the noise schedule function in LCM to align with the PIXART noise schedule, which features a higher signal-to-noise ratio during the distillation training. This adjustment allows PIXART to parameterize a broader range of noise distributions, further enhancing image generation. Section Summary. In this section, the authors propose PIXART, an advanced text-to-image synthesis model that incorporates LCM and ControlNet. LCM is used to accelerate the inference process by solving an augmented probability flow ODE, resulting in faster generation while maintaining high-quality images. ControlNet, on the other hand, is a module that provides superior control over the generated images, and the authors propose a customized ControlNet transformer architecture for the transformer model used in PIXART. Section. Training efficiency and inference speedup. We've managed to train our model, PIXART, efficiently within the constraints of a 32 GB GPU memory, while maintaining the same batch size and supporting image resolution up to 1024 by 1024 pixels using SDXL LCM. This efficiency allows PIXART to be trained on a variety of consumer-grade GPU specifications. Our method also makes it possible to use larger batch sizes even on GPUs with limited memory capacity, which is beneficial as larger batch sizes can improve the training process. When it comes to generating images, our model consistently outperforms other methods like SDXL-LCM LoRa, PIXART, and the standard SDXL across different hardware platforms. For example, PIXART can generate high-resolution images of 1024 by 1024 pixels in less than half a second on an A100 GPU, and in just over 3 seconds on a T4 GPU. This is a significant improvement over other methods, which can take up to 26.5 seconds on a T4 and 3.8 seconds on an A100. Furthermore, PIXART requires less than 8 GB of GPU VRAM, thanks to the implementation of 8-bit inference technology. This efficiency allows PIXART to operate on a wide range of GPU cards, and even opens up the possibility of running on a CPU. In terms of training details, we conducted our experiments in 2 resolution settings, 512 by 512 and 1024 by 1024 pixels, using a high-quality internal dataset with 120,000 images. We were able to train the model smoothly in both resolutions using the multi-scale image generation capabilities of PIXART. For both resolutions, PIXART produced impressive results before reaching 5,000 iterations, with only minimal improvements observed thereafter. The training was executed on 2 V100 GPS with a total batch size of 24, a learning rate of 2E5, an EMA rate of 0.95, and using the AtomW optimizer. We used the DDIM solver and a skipping step of 20 for efficiency. In terms of architecture, we initially tailored ControlNet for the UNet architecture, which used skip connections to enhance the integration of control signals. However, incorporating ControlNet into transformer-based models, like PIXART, presented a unique challenge. Unlike UNet, transformers don't have explicit encoder and decoder blocks, making the conventional connection between these components inappropriate. To address this, we proposed an innovative approach, ControlNet Transformer, to ensure the effective integration of ControlNet with transformers. This preserves ControlNet's effectiveness in managing control information and high-quality generation of PIXART. PIXART contains 28 transformer blocks. We replaced the original zero convolution in ControlNet with a zero linear layer, that is, a linear layer with both weight and bias initialized to 0. We treated the first 14 blocks as the encoder level of PIXART, and the last 14 blocks as the decoder level of PIXART. We used ControlNet to create a trainable copy of the 14 encoding blocks. The outputs from these blocks were integrated by addition into the 14 skip connections, which linked to the last 14 decoder blocks. However, this adaptation, referred to as ControlNet UNet, encountered challenges due to the absence of explicit encoder and decoder stages and skip connections in the original transformer design. This adaptation departs from the conventional architecture of the transformer, which hampers the effectiveness and results in suboptimal outcomes. To address these challenges, we proposed a novel and specifically tailored design for transformers, ControlNet Transformer. This innovative approach aims to seamlessly integrate the ControlNet structure with the inherent characteristics of transformer architectures. To achieve this integration, we selectively applied the ControlNet structure to the initial base blocks. We generated trainable copies of the first base blocks. The output of each trainable block is intricately connected to a zero linear layer, and the resulting output is then added to the output of the corresponding frozen block. This combined output serves as the input for the subsequent frozen block. This design adheres to the original data flow of PIXART, and our observations underscore the significant enhancement in controllability and performance achieved by ControlNet Transformer. This approach represents a crucial step toward harnessing the full potential of transformer-based models in such applications. Section Summary. The paper discusses the training efficiency and inference speedup of the PIXART model. For training, the distillation process is successfully conducted within a 32 GB GPU memory constraint, allowing for a wide range of consumer-grade GPU specifications. In terms of inference, PIXART achieves high-resolution image generation in a significantly shorter time compared to other methods, making it efficient and compatible with various hardware platforms. Additionally, the paper introduces 2 architectures, ControlNet UNet and ControlNet Transformer, to effectively integrate control signals with the transformer-based PIXART model, resulting in improved controllability and performance. Section. Experiment Settings. In our experiments, we used a head-edge map from PIXART as the basis and carried out a detailed study on 512px generation, with a particular focus on variations in network architecture. We examined both the ControlNet U-Net and ControlNet transformer. We plan to explore other conditions, like CANI, in future research. For the ControlNet transformer, we tested different numbers of copied blocks, including 1, 4, 7, 13, and 27. We obtained the head from our internal data, and we followed the advice that a larger gradient accumulation, set at 4 in our case, leads to better results. We used the same optimizer and learning rate as in PIXART. We carried out all our experiments on 16 V100 GPS with 32 GB. The batch size per GPU for the ControlNet transformer experiment, where the number of copied blocks, n, equals 27, was set at 2. For all other experiments, we used a batch size of 12. Our training set was made up of 3 million head and image pairs. In our detailed study, we found that the ControlNet transformer generally performed better, showing quicker convergence and improved overall performance. This superior performance can be attributed to the fact that the design of the ControlNet transformer aligns well with the natural data flow of transformer architectures. On the other hand, the ControlNet U-Net introduces a conceptual information flow between non-existent encoder and decoder stages, which deviates from the transformer's natural data processing pattern. In our study on the number of copied blocks, we found that for most scenarios, such as scenes and objects, good results can be achieved with just one copied block. However, in more challenging edge conditions, like the outline edge of human faces and bodies, performance tends to improve as the number of copied blocks increases. Balancing computational load and performance, we found that 13 copied blocks is the optimal choice for our final design. We also analyzed the effect of training steps. We found that convergence is very fast, with most edges achieving good results at around 1,000 training steps. We also noticed a gradual improvement in results as the number of training steps increased, particularly in enhancing the quality of outline edges for human faces and bodies. This observation highlights the efficiency and effectiveness of the ControlNet transformer. We observed a similar, sudden convergence phenomenon in our model, as also seen in the original ControlNet work, where it quickly adapts to the training conditions. This typically occurs between 300 to 1,000 steps, with the convergence steps being influenced by the difficulty level of the specified conditions. Simpler edges tend to converge at earlier steps, while more challenging edges require additional steps for convergence. After sudden convergence, we observed an improvement in details as the number of steps increased. Building on the powerful text-to-image generation framework of PIXART, our proposed PIXART ControlNet extends these capabilities to produce high-resolution images with a high level of control. This is clearly shown in the detailed visualizations presented. Upon closer inspection of these figures, it is clear that PIXART ControlNet can exert precise control over the geometric composition of the resultant images, achieving fidelity down to individual strands of hair.